All right, let's go to number 9. So number 9, the function is x squared e to the x 2x. What kind of a function is this? It's, I mean, you do have a composition in the part e to the 2x, but overall this is a product. So we are going to use the product rule. And so the product rule says the derivative of the first times the second plus first times the derivative of the second. So according to that, it's 2x times e to the 2x. That's the derivative of the first times the second, plus first times the derivative of the second. This is where the chain rule has to be implemented. It's e to the 2x times the derivative of 2x, which is 2. Okay, so now we have, we can sort of factor out 2x e to the 2x, which is this whole thing. So that becomes 1 plus, oops, we can't do that, can we? All right, so let's move out. What we can factor is x times e to the 2x, which appears in both. And then you have 2, and then plus x, because that's what you have when you divide this by x e to the 2x, you have 2. When you divide this by x times e to the 2x, you get simply, you do have 2, right? So let's put 2 here. All right, so it's 2 times x to the e to the 2x. And so 2x e to the 2x, that's this whole thing. So the remaining part here is 1. And then you have 2x e to the 2x. If you divide this by that, you simply have 1x left in. So that will be your answer. All right, number 10. Oh, by the way, if you left it like this, I guess that's okay. It's acceptable. Although I do prefer that you factor out and make your answer look simpler. All right, number 10, f of x is e to the, what in the world is that? A square root of x. You can write this as e to the x to the 1/2. Clearly, it's a composition of functions, multiple functions. All right, the first thing is, if what you have is e to the blob. All right, so that becomes e to the blob. It doesn't change. Remember, wonderful, wonderful property of the number e. So e to the blob becomes e to the blob after differentiating. And now we have to take the derivative of the blob, which is this. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2, which this whole thing can be written as 2 square root of x in the denominator. That would be this whole thing. And then e to the square root of x. So if you do that, you will get your answer. Number 11. F of x is x plus 1 over 2x minus 3. That's just a simple rational expression, right? Rational function, polynomial over a polynomial. You use the quotient rule, of course. The denominator, the first thing I do, by the way, when I use the quotient rule is to draw this long, long horizontal line, because you know that the expression is going to be very long. All right, I like to work on the denominator first, which is basically the original denominator squared. Remember, it's g squared in the denominator. The numerator is the derivative of the top, which is 1, times 2 minus x, which is the denominator, minus the top times the derivative of the denominator, which is 2. All right, this definitely you should simplify. 2x minus 3 minus, let's see, 2x, and then you have negative 2 times negative, so it's positive 2. The denominator doesn't have to be multiplied out. In fact, I think factored form is nice. But the numerator, well, 2x and 2x cancel out. Negative 3 plus 2 is negative 1. Okay, so this is much simpler, and I would recommend it. Of course, it's okay if you write this as, you know, if you multiply this out, it's 4x squared minus 12x plus 9. That would be fine too. Either one would be okay here. Okay, let's go to number 12. F of x is natural log of 3x to the 7th power. Now here you have several functions composed together, but the outermost function, the last thing you do is the 7th power, right? So you take 7 times the blob to the 6th power, and then you work your way in. So now we are ready to take the derivative of the natural log of 3x. So that becomes 1 over 3x. But because 3x is a function itself, and in this case, the innermost function of the 3, See, what happens is x becomes 3x. That's the first thing that happens under this operation. And then you take the natural log of it, and then you take the 7th power. So when you take the derivative, you do the 7th power first, and then you take the natural log of 3x and differentiate it. And then you differentiate, you multiply to that the derivative of the innermost function, which is 3. So of course, this will cancel. And so this just becomes 7 natural log of 3x, the whole thing quantity, to the 6th power, and then you have x in the denominator. Okay, we'll do one more, and then we'll go into the next part, next clip of the video. All right, so number 13 is a special one. Okay, now why is that? Well, you can't just simply, you cannot apply the power rule because you have x in the base and x in the exponent, right? So what do you do when you have x both as a part of the base and as a part of the exponent, right? This is a situation that, you know, calls for what? Logarithmic differentiation, which is a type of implicit differentiation. So take ln of both sides. Okay, that's a recommendation. That's a tip, a hint. So when you take the ln, let's write y on this side. Ln of y is equal to the ln of x to the x plus 2. But remember, if you have ln of a to the bth power, that b, the power, becomes an exponent, not the exponent, the power. The exponent becomes a coefficient. And this is what happens. This is how you transform a log, right? And because of this property of logarithm, that's why we can do this logarithmic differentiation. Okay. Now, when you take the derivative of this, this becomes 1 over y, but that's not it, right? Because y is a function of x. So this is like log of a function itself. Y itself here is like a blob. So you take the derivative of y, which is y prime. It's good to have the y prime here because that's what we are trying to solve for. Ultimately, we want y prime to be by itself on this side. Now, you have a product here. So let's take the derivative of the first times the second plus the first times the derivative of the second. Okay, we can simplify this. This is ln of x plus 2 over x. All right, now the last thing we do is to multiply both sides by y, right? Because this is the thing that I need to eliminate. And so multiply by y, but y is this. Okay, so it's x to the x plus 2. And then multiply this by the whole right-hand side, which is log of x plus 2 all over x. Now here, when you do logarithmic differentiation, typically, you only see x on the right-hand side, and you should, right? Because the right-hand side should not depend on y. Sometimes in implicit differentiation, you will see y, but not in this case. So that's what you will have. Now, there is a different form. You can do this, but of course you can separate this into two parts. So log of x plus, you know, what's x plus x? That's 1. And so if you separate the second and the third, well, you know, this term and this term if you separate this into 2 terms, as we did here, that's also acceptable. So this is fine. This is also fine. You know, either one would be okay here. All right, now let's go to 14. But before that, I will stop this video and then go to the next segment.